Good morning, good afternoon, wherever you are. I am Jeffrey Zhang. I'm a distinguished engineer from Juniper Networks. Today, I'm going to talk about multicast in segment routing networks. Agenda. So we're first going to review the SR principles and available options for multicasting SR networks. Then we will talk about controller signals, P2MP tunnels, followed by BGP signal multicast. We will talk about inter-region end-to-end multicast and multicast integrated with Classful Transport. So segment routing principles. There are two principles here I want to talk about. The foremost one is no per flow or per tunnel state inside the network. Instead, the packets have embedded segment list for traffic steering. The second option is that optionally and preferably, we will use controllers. The controllers will instruct ingress routers to embed segment lists in packets for the traffic steering purposes. Now, apply that to multicast. For the first one, no per tree state inside network. There are two options for that. The first one is ingress replication, which has been used for a long time, actually. As indicated in the upper right picture, the ingress router will send multiple copies to individual edge receivers. Obviously, this does not have efficient replication inside the network, but it does not incur per tree state inside network. It works for some use cases. The second one is BIR, Bit Index Explicit Replication. It is a new multicast technology that gives you efficient replication without requiring per tree state inside the network. Basic idea is that packets carry a bit string indicating where the traffic should go, and then the internal routers, transit routers, will figure out how to replicate towards those indicated edge routers efficiently. Because it does give you efficient replication and does not require per tree state in the network, it is the best multicast technology so far, whether it's for SR network or not. However, because it involves a new forwarding plan, so its deployment has been hindered, and we are actually not going to cover it in today's presentation. I want to point out both ingress replication and BIR, while they match the SR principle number one very well, they are actually all independent of SR. You can use them in a non-SR network as well. Principle number two, use of controllers. So there are two flavors of this. The first one is the controller only does the calculation. It calculates a P2MP tree and then send the explicit paths to the tunnel ingress, who will then use traditional RSVP TE P2MP signaling to set up the tunnel. The second flavor is that controller does everything. It does the calculation and it does the signaling. And for that, there are also two flavors. One is that we call SRP2MP, or previously known as tree-state. The second one is MLDP, and we'll talk about those a bit more later. I want to emphasize here that all these options here have identical forwarding plane, as with legacy MLDP or RCVP TE P2MP tunnels. You will have per tunnel state inside the network, and you will have incoming traffic with labels, and you will replicate those traffic out. So to review, Here are the multicast options in an SR network. If you care about effective replication and you don't want to have poor trace state in the network, and most of your routers can support beer, then the beer is best option. If you cannot do that, then traditional multicast may work well for you, whether it's PIN, P2MP tunnel, or ingress replication. For example, you don't need a controller, and you don't mind running PIN, MLDP, or RSVP, those traditional multicast protocols in your SR network. I want to point out that while you're running SR unicast, it's still perfectly okay to run those traditional multicast protocols as long as you don't mind. But if you need controller calculated trees or you want to remove those legacy protocols from your SR network, then you can do controller signal multicast. Just bear in mind that with controller signal multicast, you will still have per tree or per tunnel state inside network. Now let's talk about controller signals P2MP. The first option of controller signal P2MP is SR P2MP, or previously known as tree seed. It's now being worked on in IETF various working groups. The basic idea is that the controllers will do a tree calculation and send forwarding states to each tree node of that tree to set up forwarding paths. The forwarding states for a particular node on a particular tree, we refer it to as replication segments. A replication segment is identified by the root ID, tree ID, candidate path, and targeted node. And the forwarding information includes incoming label or incoming SID, and a bunch of outgoing label or outgoing SID to replicate traffic to. From the controllers to the tree nodes, the signaling could be done by PSAP, by BGP multicast, or BGP SRT signaling. And in this presentation, we are going to focus on BGP multicast. The second option of controller signaled P2MP is MLDP tunnel that is signaled by BGP from the controllers. I want to point out that here the only relevance to MLDP is that we use the MLDP FAC to identify the tree in the control plane. Notice that in the forwarding plane, it's just like SRP2MP or legacy MLDP. So while we use the MLDP FAC to identify the tree in the control plane, we actually do not use LDP signaling anymore. The reason to do this MLDP tree identification includes that it allows easy transition from existing MLDP deployment. For example, if you already have a BGP-MAPN deployment with MLDP tunnels, then all you change is how this MLDP tunnel are set up. There's no change on the MVPN part. Another benefit of using MLDP FAC as tree identification is that MLDP FAC has this opaque structure, so it gives you a lot of flexibility and extensibility when it comes to identify a tree. Now, the signaling of MLDP tunnel using BGP multicast can actually be done either from controllers or using the traditional hop-by-hop signaling from leaves towards the roots. Now, let's focus on BGP signaled multicast. BGP-MCAST signaling basically use a new BGP Sapphire called MCAST tree Sapphire to signal SRP2MP tunnel or MLDP tunnel or IP multicast or any potential future new types. we just use a different NRI type to signal different trees. Then the rest of it will be identical, no matter what kind of tree we're setting up. The signaling can be from controllers, or can be from the leaf towards the root, hop by hop. There are different IETF drafts specifying the procedures for those two options. A little bit more details here. So in the upper right corner, we have part of the BGP update where we have NRRIs, network layer reachability information, that encodes the tree identification. For different trees, we will use different NLRI route types. For example, we can have a multicast tree, IP multicast tree that is identified by source group. And we can have a SRP2MP, a tunnel, and the NRI will encode candidate path, root ID, and tree ID. And if it's a MLDP tunnel, we will just encode MLDP fact there. The next piece of information in the NRRI is the targeted router. If you look at the picture, the controller is the button to the left of that picture. That controller calculates the tree and sends the forwarding information to different routers. Let's say R1 is a node on the tree, then the controller will send a route towards R1. That route will encode the tree identification and also encodes R1's identification, because that particular route is for R1 itself only for the multicast tree, specifying the forwarding information on R1 for that tree. We will also have a tunnel encapsulation attribute that encodes the forwarding information. That tunnel encapsulation attribute, or TEA, basically encodes a list of quote-unquote tunnels. Each tunnel will then identify the upstream or downstream information. We'll talk about that in the next slides a bit more. And finally, we also have route targets to control the propagation and importation of that route. For example, the route that the controller signals for R1 will not be sent towards R2 or R3 because of this route target. Now, the tunnel encapsulation attribute, or TEA, as we mentioned, it just encodes a list of tunnels, which could be of different tunnel types. That's already specified for unicast. And in unicast, matching traffic will be load balanced out of one of the listed tunnels. Now, when we extend this to BGP multicast, the matching traffic will be replicated out of all the listed tunnels. And we also added a new tunnel type we call any encap. It basically says that any way of getting to that tunnel endpoint is fine, whether it's native forwarding because the upstream and downstream nodes are directly connected, or it could be MPOS, LSP, GRE tunnel, SRP2P path, or whatever, it's fine. As long as you can get me to that tunnel endpoint, that's fine. Now, a tunnel in that TEA could have sub-TLVs to encode more information. For example, you could have an RPF sub-TLV indicating that this particular tunnel is for receiving traffic from upstream. You could have a tree label, a tree state sub-TLV to specify the incoming or outgoing label, tree label. You could have an endpoint address that identifies the downstream node or link. And in some other more complicated scenarios, you could have more sub-TLVs specify more information. We have a simple example here. The TEA has 4 tunnels. The first one has an RPF sub-TLV indicating that this is to specify upstream information for incoming traffic. And then tunnel 2, 3, 4, there are 2 different downstream nodes, and with the same or different tree label there. So With this tunnel encapsulation attributes alone, we can create forwarding state uh, for the tunnel that is identified in the NRI. Now, so far we sort of assume that the forwarding plane is MPLS, but this SR MPLS or SR P2MP or SR or MLD P2MP, they work for both MPLS and SRv6 forwarding plane. We just need minimum differences or extensions in the tunnel encapsulation attribute to make it work for SRv6. In case of MPLS forwarding plane, the forwarding onto a branch uses a transport label followed by a tree label stack. The transport labels will get a package to the downstream node. It could be either explicitly encoded in a TEA tunnel or derived from the tunnel endpoint listed in that tunnel. The transport labels could also be empty. For example, the upstream and downstream nodes are connected directly. It could be also an SR path, or it could even be a label that represents a P2MP tree or subtree. That is just like the traditional MLDP over RCVP P2MP tunnel case. And then in case of SRv6 forwarding plane, the above mentioned label stack will become an IPv6 address. Remember that in the SRv6 forwarding plane, an IPv6 address is now divided into a locator ID part and followed by the function and argument part. So in this case, the locator ID part will represent the downstream corresponding to the transport labels. That is responsible for getting the traffic to that downstream node. And the function and argument part of the IPv6 address will represent the tree corresponding to the tree label. So you can see that the same signaling will work for both MPLS and SRv6 forwarding plane. So in this presentation, we are focusing on BGP-MCAST signaling because we believe it's the best option. For example, if you compare it against PSAP, if you're using BGP signaling from the controller, you only need one session to one of the BGP speakers in the network. If you use PSAP, you will need one PSAP session to every tree node. Additionally, the BGP signaling has great coverage and extensibility. As you already see, we are using the same BGP-MCAST signaling procedures and encoding to signal both IP multicast tree, SRP2MP tunnel, MLDP tunnel, or possible future extensions. And in some cases, we can even use this BGP-MCAST to replace BGP-MAPN in some scenarios. And this same procedure can be used for both underlay tunnel signaling and overlay multicast tree setup. It already specified how the bidirectional tree can be supported. It works for both hub-by-hub signaling or controller signaling. And it also easily fits into the end-to-end interregion multicast tree framework and also integrates very well with Classful Transport, which we will be talking about in the next follow-up slides. So now let's talk about end-to-end interregion multicast. A multicast tree can span multiple regions. Here, a region could be an AS, autonomous system, or it can be an IGP area. And you can use different signaling in different regions. Between the regions, we have these routers called RBRs, or regional border routers. And for a particular region, we can do either in-band signaling or overlay signaling. With in-band signaling, The internal routers in the region will maintain state for those individual end-to-end trees. But with overlay signaling, the internal routers will not keep state for the end-to-end trees. Let's take a closer look at in-band signaling across a region. Remember that we can have different methods used in different regions. In this picture, you can see that we have the roots in the metro region 1, leaves in metro region 2. Now, it could be that we have the multicast tree is IP multicast identified with source group, and in the metro region 2, we are doing PIM signaling. When it comes to core region, we're doing MLTP in-band signaling. We'll have one MLTP tunnel for each of those IP multicast trees. And when it comes to metro region 1, we switch to BGP signaling, and whether it's controller-based or hop-by-hop signaling. Another example is that in the metro region 2, we can have SR P2P tunnel set up by PSAP. When it comes to core region, we'll do BGP-MCAST signaling for the same SR P2P tunnel. And in metro region 1, someone said, I want to do BGP SRTE signaling for that. And finally, for in the metro region 2, you could be doing the legacy MLTP signaling for MLTP tunnel. In the core region, we can do the BGP-MCAST signaling from controllers to set up the MLTP tunnel. And in region 1, we'll use BGP-MCAST signaling, but to do the hop-by-hop fashion. Now, in case of hop-by-hop signaling, a router needs to determine its reverse pass-forwarding neighbor, basically the next hop neighbor towards the tree root. So it needs to have a route towards the root. In the inter-region case, for example, seamless MPLS or seamless SR, it's quite often that internal routers actually do not have the route towards the tree roots. In that case, the RPF needs to be towards the upstream RBRs instead. And for that, if PIM signaling is used, then the PIM RPF vector can be used to encode the upstream RBR. If it's MLDP signaling, then MLDP recursive flag can be used. These are all existing RFCs. Now, for BGP-MCAST signaling, similarly, we introduced this RPF address extended community to encode the same information. Now, with overlay signaling over a region, the internal routers do not keep state for the end-to-end trees anymore. Instead, the regional border routers will signal to each other directly over targeted LDP sessions or over BGP sessions. There are three options here. The overlay signaling could be BGP FVPN specified in this RFC 6514, or could be done by MLDP over targeted sessions specified in RFC 7060. And finally, it can also be used for can use BGP-MCAST signaling. Now notice that when we use MLDP or BGP-MCAST, there is actually no difference between overlay and in-band signaling anymore. It's just whether the downstream, upstream nodes are directly connected or not. In this picture, the RB1 and RBR1 and RBR2 are not directly connected. RBR2 send signaling to RBR1 directly, and then RBR1 will tunnel the traffic to the downstream RBRs, either via ingress replication or via P2P tunnels. However that P2P tunnel is set up is fine. Finally, let's talk about multicast with Classful Transport. Classful Transport is a new topic that is ongoing in the IATF. Basic idea is that in operator network, the underlay routes are classified into transport classes. For example, we have red transport class, blue transport class, and green transport class. Those underlay routes are advertised with this new CEFI called Classful Transport CEFI, and the routes are attached with transport class route targets. The route target specifies the transport class also controls route propagation and importation. And the service route or overlay routes will carry a mapping community that will map to the transport class that is used to resolve the protocol next hop. So that's the basic idea of this BGP Classful Transport framework. Now, multicast can easily fit into that picture. For example, a multicast tree or a multicast tunnel could be an underlay one for a particular transport class, or it could be an overlay one using a particular transport class. Either way, when we use BGP-MCAST signaling, the BGP messages can carry a mapping community for the transport class, and that will affect the selection of paths or tunnels between an upstream and its downstream nodes. It could also affect the selection of the upstream node on a downstream node. In summary, we looked at principles of SR networks and various options for multicast in SR networks. Those options could be per SR principles or not. Mainly it's basically per deployment considerations. In the non-beer, non-traditional options, we believe BGP multicast is the best option. It only needs one single session from the controller to one of the BGP speakers, and it offers great coverage and extensibility. In particular, if you already have a MLDP deployment, then using BGP signaled MLDP will make the transition a lot easier. And also, because of the flexibility and extensibility due to opaque nature of MLDP FAC, that will make the tree identification a lot easier when you use MLDP FAC to identify the tree. So an end-to-end multicast tree or multicast tunnel, they span multiple regions. You can use different signaling methods in different regions, and BGP signaling is one way to stitch everything together. Especially in the inter-region case, BGP is like the universal language here. And finally, BGP-MCAST signaling can easily integrate with classful transport concept.
Well, that was one of the more in-depth presentations about multicast I've ever seen. So let's see what we have for questions. The answer is nobody's asked anything. Do you have a closing comment? Anything you've thought about since you did the presentation?
Actually, no. I hope people may find this information useful. I'm always happy to have follow-up discussions anywhere, in IETF or through our customer connections.
Through customer connections, and your email address is readily available.
Yes.
Thank you very much.